Hello everybody. In this video I am going to present a completely new and non-Newtonian proof of Sir Isaac Newton's law of universal gravitation. Modern day proof of Newton's law of gravitation is based on vector calculus and differential geometry, making it complex and inaccessible at the high school level. Newton's own method was geometric, which, though elementary, is by no means simple, making this too inaccessible to high school students. Here I am going to present a proof that is both elementary and simple, accessible to even high school students. The proof is algebraic, and if you know elementary calculus and know how to solve a quadratic equation, then you are mathematically overqualified to appreciate this completely non-Newtonian method of proof of Sir Isaac Newton's universal law of gravitation, which, as far as I know, is completely original and not found anywhere else previously. The proof begins by assuming the very plausible assumption that path of planetary orbit around the sun is an ellipse, and then showing that the assumption is internally as well as externally consistent. If Newton's law of gravitation, as we know it, is assumed to be true. Besides all this, a simple, intuitive, and already widely accepted proof that in classical mechanics every result is 1 1 and unique with every initial condition. That is, in a more concrete terms, knowing the value of the initial position and velocity of a planet, it follows a unique and deterministic future, what may be summarized as uniqueness of physical laws on initial condition. So, we are going to assume, based on Kepler's observation, that the path of planet around the sun is an ellipse. So now we'll draw that ellipse. So this is the ellipse. Now, this is the major axis whose length is A, sorry, 2A. And this is the minor axis whose length is 2B. So semi-major axis has a length of A and semi-minor axis has a length of B. Now, let's say that this is the foci F1 and symmetrically to the other side there is another foci F2. So F1 and F2 are the foci and the sun is at one of the foci. So let's say sun is over here. The planet, let's say, is at this point initially at time t is equal to 0, and this is the velocity vector at that instant. Now, this distance is AE, where A is the semi-major axis and E is the eccentricity. This velocity is V naught, And this distance from the sun, that is from the focus F1, is R naught. This is R naught. Now at a general time, let's say the planet has moved to this point, and this is the radius vector. We'll let this be equal to R, and this is the angle theta at a general instant of time. This was at t is equal to 0, and this is at t is equal to t some general time. Now, at some point of time, the planet will be at this point. Then the velocity vector will be like this. So this is the velocity vector v. Now, this one is semi-major axis, semi-minor axis, sorry. This one is semi-minor axis. So this length is b. And we'll join this again by a straight line. So I have joined this. And then this is a right triangle, this angle being 90 degree. So this one, we'll let it be denoted by R dash. We'll let this be denoted by R dash. And where R dash by Pythagoras theorem will be under root of b square plus a square e square. So that's the diagram. Now, since the torque due to a central force on a planet, gravitation being a central force, so the torque will be 0, and therefore angular momentum will be conserved. So we'll conserve the angular momentum about these 2 points. Let's say that this is point number 1 and this is point number 2. We can conserve it at about any 2 points. But for our purpose, these 2 points are appropriate for the calculation that follows, that is going to follow. So, from conservation of angular momentum, from conservation of angular momentum, we have initial angular momentum is, let's say that the mass of the planet is small m and mass of the sun is capital M. So that the planet's angular momentum at point 1 about the sun, and we have taken the origin also at the sun. So it would be m v naught r naught, because r naught is the perpendicular distance of this point. Since we're taking this as origin, let's also denote it by O. So m v naught r naught. R naught is the perpendicular distance of O from the velocity vector v naught at point 1, that is at initial time. So the angular momentum is linear momentum m v naught times r naught. And at point 2 we have the angular momentum as m into v. This is the linear momentum into the perpendicular distance of O from the velocity vector. So that is just this distance, which is b. So we'll write it as mvb. So this m cancels, and from this we have v is equal to v naught r naught upon b. So we call this equation number 1. Now I'll do it here. Now from conservation of total mechanical energy, from conservation of total mechanical energy, TME, which is total mechanical energy has two parts obviously. One is the kinetic part and another is the potential energy part. So the potential energy at point 1 is minus g m m over r naught, and the kinetic energy is half small m v naught square. Finally, the potential energy at point number 2 is minus g m m upon r dash, plus the kinetic energy is half m v square. Now we'll simplify this. So this becomes minus g m m over r naught plus half m v naught square is equal to minus g m m over r dash. Will take this one. So this would become under root of b square plus a square e square, plus we have half m. V will take from equation number 1. So equation number 1. So we'll write it as, we'll also have to square it. So it will be v naught square r naught square upon b square. So this is what we have. Now we'll write this as minus g m m over r naught plus half m v naught square is equal to now we will use a relation that b square, I need space, so right here, put it in a box. We have b square is equal to a square into 1 minus e square. This is simple mathematics. It is a property of ellipse. E is the eccentricity, A is the semi-major axis, and B is the semi-minor axis. So out here we have under root of b square plus a squared e squared. So this simplifies to under root of b square plus a square e square. This is what we have to find out. This will be equal to under root of b square will substitute as a square into 1 minus e square plus a square e square. It's all under the root, square root. So what we have is uh, a will come out of the square root sign, and inside will be left with 1 minus e square plus e square. So that just cancels and just 1 is left. So under root of 1 is 1. So this full thing is equal to a. So we can substitute. So this becomes then, we can substitute here. So this becomes minus g m m over a plus half m v naught square r naught square v naught square r naught square upon b square, again will substitute as a square into 1 minus e square. Yeah. So in this formula b is completely eliminated, and the characteristic variables of an ellipse in this formula are a and e. So a gives the size of the ellipse and e measures its eccentricity, that is the shape of the ellipse. So I'll now erase this one because I need space. So now this entire equation, the last equation that we have, that is this one, can be treated as a quadratic equation in 1 upon a. So I'll rewrite it in a proper manner. This equation then becomes minus m, sorry, not minus, just plus m v naught square r naught square upon 2 into 1 minus e square into 1 upon a whole square. The second term would be minus g m m into 1 upon a, and the last term would be within bracket g m m over r naught minus half m v naught square. So we can say that it is a quadratic equation in variable 1 upon a. Now we are going to invoke the uniqueness condition. Since for a given initial condition, the outcome must be unique. Therefore, for uniqueness of physical laws, we must ensure that the variable 1 upon a has got a unique value. But this is a quadratic equation, so this is going to give us two values. So when does a quadratic equation give only one value, a unique value? When the discriminant is 0. So what we do is that we write that for uniqueness, we set the discriminant of this quadratic equation d to be equal to 0. So d is 0 means b square minus 4ac. This is the discriminant. This should be equal to 0, which implies that b square, the coefficient of 1 by a term, the square of that, should be equal to 4 times the coefficient of 1 by a whole square term and the last constant term c. So this will be equal to 4ac. So we'll write the quadratic equation over here, general form. This is a x square plus b x plus c is equal to 0. Out here also we had a 0. I just missed that point. This was 0. So by comparing, we can find what are a, b, and c. X is of course 1 by a. Now, b squared is nothing but a square of minus gmm, so it is g m g square m square, capital M square, and small m square. This is our b square. And for 4ac part, we have 4 into a will write as m v naught square r naught square upon twice 1 minus e square. So this is our a term. into the C term would be the quantity in the last bracket. It would be G M M over R naught minus half M V naught square. So this is what we get on equating the discriminant of the quadratic in 1 by A to be equal to 0. Now I need space, so I'll erase this one. So now if I simplify the last expression, at this place, this 2 cancels with this 4, so it's 2 over here, 2 to the 4. Then this m square cancels with this m, and this m taken common from these two expressions. So these are cancelled. So we can now write it like this by cross multiplying. We can write it as 1 minus e square, e being the eccentricity of the ellipse, is equal to 2 v naught square r naught square upon g square m square into g m over r naught minus v naught square upon 2. Close the bracket. Then we can open up the bracket and write 1 minus e square is equal to 2 g m, capital G being the universal gravitational constant, by g square m square r naught square v naught square and r naught in the denominator. Then we have minus of r naught square v naught 4, r naught square v naught 4 upon g square m square. Now this simplifies to after some cancellations, obvious cancellations. This simplifies to e square is equal to 1 minus 2 r naught square v naught square by gm plus r naught v naught square by gm whole square. The obvious cancellations over here was just g cancels with this one of the g and one is left. This m cancels with one of them and one is left. And this r naught cancels with this r naught and one was left. And then we had this equation, the later one. So this is what we have for e square. Now we write this e square as equal to 1 minus r naught v naught square by gm whole square. So for eccentricity, we have the following formula. I need space, I'll erase this one. So I have now E is equal to plus or minus, because we're taking a square root of both sides of the last equation, of 1 minus r naught v naught square by gm. Now if we assume that v is greater than or equal to v naught, sorry, v is greater than or equal to v naught, then when it is greater than v naught, as it tends to be greater than v naught, the velocity at this point, for v is equal to v naught, the eccentricity is obviously for just a moment. If we assume that V naught if we assume that V naught is equal to under root of Gm over R naught, then this is nothing but orbital velocity of a satellite in a circular orbit. So the eccentricity would be 0. That's okay, because if we put V naught is equal to under root of Gm over R naught, over here this thing will become equal to 1, and 1 minus 1 would be 0, so eccentricity is 0. But if V naught is greater than this value, then the eccentricity becomes negative. So we'll have to choose a negative sign in order to uh, arrange for that case. So we'll have to arrange this formula like this, choosing negative sign for V naught greater than or equal to under root of G m over R naught. So the formula for eccentricity we have then is, if we choose the negative sign and if we open up the bracket, E becomes equal to R naught V naught square over G capital M minus 1. Now this indeed is the expression for eccentricity of planetary orbits. So it's externally consistent. And now we're going to make a consistency check, the inner consistency check, that all these are also internally consistent. So that consistency check goes like this. I need space, so I'll free space now. This was a major axis. It got erased accidentally earlier. So if we assume this point to be the origin and the sun being at the foci, which is assumed to be the origin, then the equation of the ellipse in polar coordinate is the following one. It is r is equal to 1 plus e being the eccentricity, into r naught upon 1 plus e cos theta. This is the polar equation of the ellipse. Now if we choose theta is equal to 0 degree, then this r is equal to r naught. Putting theta is equal to 0 degree in this equation, this is what we have. as can also be seen from the figure. This is R naught. And if we choose theta to be equal to 180 degree, that is when the planet is at this extreme, the opposite extreme. Then we have, and if you put theta is equal to 180 degree in this equation, cos 180 would be minus 1. So it would be having R is equal to 1 plus E into R naught upon 1 minus E. Now, so this is R naught, and this one from the opposite extreme to the foci F1, that distance is 1 plus E into R naught over 1 minus E. So if I sum these two distances up, this distance and this distance, it would be nothing but the entire major axis's length. So we'll have so what we'll do is this. We'll see whether this is equal to, we'll set this equal to, we'll add this up first. And if I add it up, if we add it up, we have 1 plus E R naught upon 1 minus E plus R naught. That's equal to 2A. So from this, we can easily show that 1 by A is equal to 1 minus E over R naught. Just simple algebra. We'll take R naught common, take the LCM and simplify, and this will be this one. It's quite trivial to show this one. Now, again I need space, so I'll erase this one. So from the quadratic equation that we wrote earlier, 1 by A would be equal to minus B plus minus square root of discriminant upon 2A. The discriminant was set to 0 for uniqueness. So if we set that equal to 0, then for 1 by A, we have minus B over 2A. So this would be the unique value of 1 by A, reciprocal of semi-major axis. So from that equation, if we substitute the coefficient B of the quadratic equation and A of that same quadratic equation, we'd be having minus of minus G M M over 2 into M V naught square R naught square over twice into 1 minus E square. So this will be equal to After some cancellations, this m will cancel with this m, this 2 will cancel with this 2, minus minus will become plus, positive, and it will become equal to gm into 1 minus e square upon v naught square r naught square. So this thing will become equal to further 1 minus e over r naught into gm upon r naught v naught square into 1 plus e. We have factorized 1 minus e square as 1 minus e into 1 plus e. Now, this thing from the eccentricity equation of the ellipse that we found out earlier, derived earlier, this thing is nothing but reciprocal of 1 over 1, reciprocal of 1 plus e. So, this becomes equal to 1 minus e over r naught into 1 plus e over 1 plus e. So this cancels, and we have therefore, I'll write it here, last step. So we have 1 by a is equal to 1 minus e over r naught, and this equation and this equation are indeed the same. So setting the discriminant equal to 0 and deriving whatever we did was all internally consistent. Now, in the conservation of mechanical energy, total mechanical energy, we used I need space, I'll erase this one. So we used the expression for potential energy U is equal to minus G M M over R. This is the formula that we use for potential energy. Now, since all this, whatever we have done is internally as well as externally consistent, so in a way, it validates this formula. Now we know that F is equal to minus of du over dr for a conservative force field, and gravitation is a conservative force field if we assume it to be inverse square law force. So we can differentiate this and we'll get g m m over r square. So that's the Newton's law of gravitation. So it is verified. It is proven rather. Okay, thank you.